Imagine this, a railway system, something we rely on, usually so dependable, suddenly facing an invisible threat, a digital one. What actually happens when hackers aren't just after data, but they target the signals that keep trains running safely? We've had warnings, Like back in December 2011, there was that incident, Northwest Rail Company, their computers were reportedly disrupted, signals affected for 2 days. Now, thankfully, that specific case wasn't safety critical, but it was, well, a real wake-up call. It showed the vulnerability. So the big question is, how do we actually protect these absolutely critical systems? They're huge, geographically spread out and built to last for decades. How do we shield them from these unseen digital dangers? Well, this deep dive is all about that. We're pulling back the curtain on how experts are building a really robust IT security framework specifically designed for railway automation. We're going to explore, the unique challenges here, why securing railways is so different. We'll look at the foundations they're building on and the specific steps being taken to safeguard our railway future. So let's start right there. If you're tasked with protecting this massive, complex system, part old, part new, where do you even begin? What makes railways such a unique challenge for security?
That's a really good starting point because you're right. It's not just like securing an office network or a typical data center. Railways are, by their very nature, incredibly distributed. We're talking thousands, sometimes tens of thousands of kilometers of track for the big operators. You just can't physically fence all that off, putting guards everywhere. It's just not economically viable. And then there's the other huge factor, the lifespan. Railway systems, the components, they're built to last. Contracts often demand support for over 25 years. That's standard. And some of the older mechanical bits, like relay interlockings, they might have been ticking along reliably for 50 years, maybe even more.
50 years, wow.
Yeah. Now, compare that to the IT security world where things change, every few months? Every year? It's constantly evolving.
It's a massive mismatch.
It really is. And interestingly, this challenge, securing long-lived distributed infrastructure, it's not totally unique to railways. Air traffic management faces similar issues, other critical sectors too. And that shared problem is actually driving some convergence in thinking about security strategies. So what we learn here often has wider applications. Now, most incidents we've seen so far, thankfully, have been more like denial of service, annoying, disruptive, causing delays.
And not catastrophic accidents.
Right. But the potential for a safety-critical incident, however small that chance might seem, that's the real driver behind all this security work.
Okay, so 25 years, 50 years. That's ancient in tech terms. It must feel like trying to bolt modern cybersecurity onto a medieval castle sometimes. A huge headache for engineers. So given how critical safety is, how have railways traditionally handled it? They must have incredibly robust safety standards already in place, right?
Yeah. Oh, absolutely. The safety culture and standards in railways are incredibly strong, built up over decades. Think of standards like EN 50159. That's for safety-related communication. It's been around since 2001, actually, and it's solid. It defines how to build what's called a safe channel. Think of it like a protected tunnel for vital messages, even if it's running over an untrusted network like the internet or a radio link.
Okay, safe channel.
And then there's EN 50129, which covers the electronic systems themselves, the hardware and software doing the safety functions. But here's the crucial point. These standards were primarily designed to deal with threats from technical failures, component faults, or maybe environmental factors like lightning strikes or floods.
Right, things breaking or nature intervening.
Exactly. They weren't really built with intentional, malicious human attacks, cybersecurity threats in mind. Now, some of the methods they use, like error checking or redundancy, might incidentally help against some attacks, but it's not their main purpose.
So something like a denial of service attack, flooding the system with junk data. That might not be covered by traditional safety rules.
Often no. Unless that attack directly and immediately causes a demonstrably unsafe situation, the traditional safety standards might not explicitly address it. They're focused on preventing accidents due to system failure, not necessarily maintaining availability during a cyber attack.
Okay, so there's a definite gap emerging between established safety practices and the need for dedicated IT security. This must be where broader industrial security standards come into the picture. Things like ISO IEC 4408, the common criteria, or maybe the ISA 99 IEC 62443 series.
Precisely. Those are the big frameworks for general industrial control system security. They're not railway-specific initially, but they provide a really solid foundation.
But how do you bridge that gap? How do you apply these general industrial standards to the very specific world of railways?
That's where some clever regulation helps. There's a European Commission regulation, number 402013, on common safety methods. It basically provides a framework that allows security risks to be treated in a very similar way to safety risks. What this lets us do is take a general standard like IEC 62443, which is becoming the de facto standard for industrial cybersecurity, and adapt it, tailor it for railway needs. We call this the IT security for safety approach. Essentially, you embed the IT security objectives and the processes needed to achieve them right into the existing technical safety reports and safety cases that railways already produce.
Ah, I see. So you're integrating it, not creating a whole separate silo.
Exactly. It avoids reinventing the wheel, which would be a massive time-consuming effort. We leverage the proven safety processes and augment them with established security principles.
That makes a lot of sense, leveraging what works. But okay, once you decide to integrate IT security, how do you actually structure this defense within such a vast system? You mentioned that onion skin model earlier.
Yeah, the onion skin model is a great way to visualize it, drawing from that EN 50159 standard. Imagine the core railway signaling application, the really critical part. You wrap it in protective layers. You place a dedicated security shell or layer between that core application and the network it uses to communicate. This shell becomes the specific thing you focus on securing and evaluating the target of evaluation in security terms.
Like a hardened perimeter around the important stuff.
Kind of, yes. And this thinking leads directly to the zone and conduit model, which is a cornerstone concept borrowed from IEC 62443. Basically, you conceptually divide the entire railway system into different zones. Think of them as secure compartments. Each zone contains assets with similar security requirements.
Okay.
And communication between these zones doesn't just happen freely across the network. It has to go through defined secured pathways called conduits.
So you control the interaction points.
Precisely. It allows you to segment the network, apply different levels of security to different parts, and tightly control how information flows. It makes managing security across a huge distributed system much more feasible.
Right. That structure seems essential. Zones and conduits, but then how do you define the actual security measures within those zones and conduits? What's the language of the building blocks of security in this context?
Good question. That's where the ISA 99 IEC 62443 framework gives us two key elements: foundational requirements, or FRs, and security levels, SLs. The framework defines 7 foundational requirements for industrial automation and control systems. Think of these as the absolute essential security capabilities, the pillars you need to build on.
Okay, what are they?
Right. So number 1 is identification and authentication control, knowing who or what is accessing the system. 2 is use control managing what authenticated users or systems are allowed to do. 3 is system integrity, making sure the system itself hasn't been tampered with or modified. 4 is data confidentiality, protecting sensitive information from being seen by unauthorized parties. 5 is restricted data flow, controlling how and where data moves within the system and network. 6 is timely response to events, being able to detect and react appropriately to security incidents. And finally, number 7 is resource availability, ensuring the system keeps functioning and critical resources aren't exhausted, say, by an attack.
Okay, those 7 cover a lot of ground. And then you mentioned security levels, SLs. How do they fit in?
Right. The security levels, SLs, they basically quantify how much of each foundational requirement you need based on the potential attacker you're trying to fend against. There are 4 default levels defined: SL1, SL2, SL3, and SL4. SL1 is about protecting against casual or coincidental violations. Think accidental misuse, someone plugging something in where they shouldn't, maybe basic malware that wasn't targeted.
Okay, the basic.
SL2 steps up to protect against intentional violation using simple means. This is your typical hacker with generic skills, maybe low resources, low motivation, perhaps trying to cause disruption, not highly sophisticated. SL3 is for protection against intentional violation using sophisticated means. Now we're talking attackers with moderate resources, maybe specific knowledge of industrial control systems, moderate motivation, more targeted.
Getting serious.
And SL4 is the highest, for protection against intentional violation using sophisticated means with extended resources. This anticipates attackers with significant resources, deep expertise in these specific systems, possibly nation-state level capabilities, and high motivation. And a really key point here, which is different from traditional safety, is how we view these threats. With safety, you often calculate probabilities, the chance of a component failing. But with intentional security attacks, especially sophisticated ones, assigning a probability is really difficult, if not impossible. How do you predict a determined attacker?
Right. You can't really put a number on human intent like that.
Exactly. So security threats are treated more like systematic faults in safety engineering. You don't try to calculate the probability. You design the system with robust defenses to prevent the attack from succeeding, or at least mitigate its impact. It's about building inherent resilience.
That's a really interesting distinction. Prevention and resilience over probability. Okay, so we have these general FRs and SLs from the industrial standard, but railways are pretty unique. How do these levels actually get applied? What looks different for a train signaling system compared to, say, a chemical plant?
That's where the tailoring comes in, and it's crucial. What we find is that many SL1 requirements at basic level actually align quite well with things railways already do for safety. Think about it. Safety systems have to be robust against operator error, foreseeable misuse, basic failures. So there's a decent amount of overlap at that SL1 level.
Okay, so some of it is covered implicitly by good safety practice.
Yes, but not all of it. When we map the SL1 requirements from IEC 6244333, which defines the system requirements, against typical railway safety cases, we find about a quarter of those SL1 requirements are not usually covered.
Oh, interesting. Can you give some examples? What kinds of things are missing from a traditional safety view?
Sure. For instance, SR 6.1 requires that authorized personnel can access audit logs, but only on a read-only basis. Basic cybersecurity hygiene, right? But maybe not explicitly mandated by a safety case focused purely on preventing accidents. Or SR 7.1, the capability for the control system to operate in a degraded mode during a denial of service event. Safety might just say fail safe, but security wants it to keep doing something useful if possible, even under attack.
Keep functioning partially, yeah.
Another one is SR 7.2, the ability to limit the resources used by security functions themselves, so they don't become a vector for attack, resource exhaustion. And SR 7.5, requiring the system to handle switching to backup power and back without messing up the security state or dropping into an undocumented mode. These are subtle, but important for resilience against attacks.
Those definitely sound like security-focused requirements, things you wouldn't necessarily think of purely from a prevent the train crash perspective, but vital for keeping the system running securely. So how are these gaps being addressed? Is there a plan to make this simpler for engineers building these systems?
Yeah. Absolutely. There's a strong proposal, and it's gaining traction, to essentially say all the SO1 system requirements from IEC 6244333 should be included by default in the system requirement specification for any new safety-related railway signaling system.
So bake SL1 right in from the start.
Exactly. The big advantage is that it would streamline certification immensely. If your system inherently meets SL1 because it's part of the baseline safety requirements, you wouldn't need a separate additional IT security certification just for SL1.
That makes a lot of sense.
And it also allows for some smart simplification from a railway perspective. For example, for foundational requirements like, say, data confidentiality or maybe resource availability, railways might decide that for signaling, SL1 is almost always sufficient. So you could define the overall SL assignments more simply. For example, maybe SL1 for railways means all 7 FRs are at level 1. SL2 might mean FRs 1, 2, 3, 5, and 6 are at level 2, but confidentiality, FR4, and availability, FR7, stay at level 1 because that's deemed appropriate for the specific risks in signaling.
So you tailor the SL definition itself to railway needs based on risk.
Precisely. It makes the application of the standard much more practical and avoids gold-plating security where it doesn't add significant value against the likely threats.
This seems like a really pragmatic approach. Okay, so let's put it all together for an engineer. If you're actually building or upgrading a railway automation system using this framework, what are the practical steps? Walk us through the process.
Right. It boils down to a structured, repeatable process. There are essentially 4 main steps an engineer or team would follow. First is system definition and zoning. You have to meticulously define everything in the system, all the hardware, software components, network devices. Then you allocate each of these objects to a specific security zone or conduit based on its function and security needs. This enforces that clear segmentation we talked about, ensuring consistent security within a zone and defining those controlled communication pathways, the conduits, to the outside or other zones.
Get the map right first.
Exactly. Step 2 is threat and risk analysis and SL assignment. You conduct a thorough analysis. What are the potential threats, vulnerabilities, potential impacts? Based on that risk assessment, you assign the target security level SL1, 2, 3, or 4 to each zone and each conduit. And as we mentioned, for railways, this might need slightly different procedures than for a fixed industrial plant because, well, trains move, and the equipment is often out in the open, less physically protected.
Makes sense. Mobility adds complexity.
Step 3 is applying standardized requirements. Once you've assigned those SLs, the beauty is you can then directly apply the standardized security requirements that correspond to that SL, drawing mainly from IEC 6244333. This is where the efficiency comes in, because it allows engineers to specify and potentially use pre-certified off-the-shelf IT security components that already meet certain SLs. You're not inventing security controls from scratch every time.
Leveraging existing solutions.
Precisely. And the final step, step 4, is evaluation and validation. Just like with safety functions, you have to rigorously verify and validate that all the security countermeasures you've implemented actually work correctly and effectively mitigate the risks you identified. This involves testing, documentation, audits, a thorough check.
So it mirrors the safety validation process in its rigor.
Very much so. It has to, given the stakes.
So looking at the big picture then, the real power of this approach seems to be this adaptation. Taking a solid industrial standard and carefully fitting it to the unique railway context rather than starting from zero, that feels efficient and smart.
It really is the key benefit. By integrating IT security into the existing well-understood safety processes, and by tailoring these established frameworks like IEC 62443, we're building a much more resilient railway system without adding an overwhelming burden. It's about making the systems robust against modern threats, protecting the operations, and ultimately protecting the safety of everyone who relies on rail travel. It's about building that defense proactively.
Well, this has been incredibly insightful. We've covered the unique challenges, the foundational standards for safety and security, how they're being bridged, the zone and conduit model, the FRs and SLs, and the practical steps for implementation. But as we wrap up, it's impossible to ignore that the threat landscape never stands still, does it? It's constantly evolving. So maybe the final thought for our listeners is this. Even with these robust frameworks taking shape, what new kinds of attacks might we see down the line? And how will railway automation need to keep adapting, keep innovating, to stay one step ahead, ensuring that safety and reliability endures? Well, that's a continuous journey, isn't it? This work is definitely ongoing, and its future looks set to be just as dynamic as the railways themselves.